Hi everyone, now we are at sequences and series, lecture number 10. So, theme number 6, I have given exercise in the last lecture. It is similar to P series test, right? So, let me continue from here. I hope you have done. Just verify your answer. So, I have taken an is this one over n into ln n whole raised p, and which is a function f of n. Similar to logarithmic, similar to P series test, it has to satisfy three conditions, right? First one, f should be continuous, right? So in what interval you have to verify? Look at the series. Look at the series. So the series here is, it is from where to where? From 2 to infinity. The series is from 2 to infinity. Look at 2 to infinity. So therefore here the integral, the limit also you have to verify from 2 to infinity. In the interval 2 to infinity you have to verify. So now clearly the function is continuous. F is continuous in that interval. That means you take any point in that interval. At that point, the function is well defined. So, for example, start with 2, substitute 2, 2 into ln 2 is well defined, 3 into ln 3, 4 into ln 4, 5 into ln 5 likewise. So, if you substitute infinity, ln infinity is infinity, 1 by infinity is 0. So, everywhere it is well defined, therefore, f is continuous. And second thing it has to satisfy, it should be positive value, right? So, it's clearly positive value. So, f is positive value. F is positive value, right? And next third one is it's supposed to satisfy decreasing. So, start with n into ln n like this, n into ln n, which is clearly less than n plus 1 into ln n plus 1, right? This is obvious. So if you raise power p, that is also similar, right? Power p. So this is power p, right? So 1 over n into ln n. Why I have written this? Because p is, look at, p is positive, right? P is positive power. So therefore this remains in the numerator itself. That's what I have written both sides power p. So ln raised p, which is more than 1 over n plus 1 into, right, ln n plus 1, ln n plus 1 raised p, raised p. So clearly, so this is an and this is an plus 1, right? So therefore it is decreasing. So clearly it is decreasing. So once it is decreasing, then I can apply integral test as what I did in P series test. Same similar thing. Okay. So therefore, what we can say? So therefore, sequence an is decreasing. An is decreasing sequence. So once it is decreasing, then all the three conditions are satisfied. So therefore we can apply integral test. Therefore by integral test, by x, because the series is from 2 to infinity. So this is integration 2 to infinity 1 over x into ln x raised p, ln x raised p into dx. Then our aim is to solve this integral. If the integral is converges, then the corresponding series is converges for p, this p more than 1. Okay. So now let's compute this. So before going to that, then go to the change of variable. So let u is some ln x. U is equal to ln x. I'm changing the variable u from where x to u. So then du is equals to 1 over x dx. And the corresponding limits, we need to compute the corresponding limits. So if x is equal to 2, look at the previous old limit. So this is x is equal to 2 from where x is equal to infinity. So if x is equal to 2, then the new limit u value is ln x, right? So ln 2. Instead of x, you substitute here 2. X is 2, therefore u value is ln 2. So then now new lower limit is ln 2. Similarly, new upper limit I need to compute. Old upper limit is infinity. So now the new upper limit u is ln infinity, ln infinity. So which is infinity. Clear? So therefore now, so the new integral is modifies like this. So integration u is from ln 2 to infinity, ln 2 to infinity. These are u limits, right? And look at the integral 1 upon x dx. What is 1 upon x dx value? Du. So let me write here du. Okay. And next ln x value is u. Then all these things you write here. So 1 upon u into du, that's it. 1 upon u power p, right? Because ln x power p is there. So therefore it is u power p, u power p, u power p. So this integral, this integral is modified as, so 1 by x dx will be du and 1 by ln x value is u, so u power p, will get 1 by u power p d. So then solve it. So this will be, so which is equivalent to u power minus p, is it, plus 1 divided by minus p plus 1, and where the limits are from u is equals to ln2 to ln just infinity. Okay, just infinity, and substitute the limits. What will you get? It will be 1 over 1 minus p, right? And infinity is 1 minus p minus, and ln2, lower limit is ln2, ln2 is 1 minus p, 1 minus p. So now here we have to invest about 1 minus p. So since what we had here is, since we are starting with p more than 1, right? So p more than 1, that means you send p to right hand side, you will get 1 minus p is, 1 minus p value is less than 0. That means what, 1 minus p is negative. So once 1 minus p is negative, look at infinity power negative number is 0. Already we discussed in p series test. So therefore this is equivalent to 1 over 1 minus p, 1 over 1 minus p, and this value is 0 minus ln2 is 1 minus p. Okay, since 1 minus p is negative, so and p is finite value, p more than 1, which is finite. So 1 minus p is also finite, ln to power 1 minus p is also finite. So this entire number is finite number. So therefore this is finite number. So therefore by integral test, this integral is, first of all, since it is finite number, so therefore the integral f of x dx from 2 to infinity, dx where from 2 to infinity, this is convert this. So therefore by integral test, so therefore for p more than 1 we proved, for p more than 1 proof is over. Next we have to do for p second one, p less than or equals to 1 case, p less than or equal to 1 case we have to prove. So let us do it by case by case. So case 1 in this, let us prove it by, for p less than 1 you prove it, p less than 1. Then take the same integral, integration 2 to infinity f of x dx, f of x dx, okay, which is equivalent to integration 2 to infinity. What is f of x here? So f of x, the limits, okay, you substitute, then I will modify 1 upon x into ln x raise p into dx. And after simplification, what I got, so this is directly I am writing answer. So 1 upon 1 minus p, look at the top of this page, the final evolution will get infinity power 1 minus p minus ln2 power 1 minus p. Okay, now in this same phenomena, here p less than 1, so here p less than 1, then if you bring p to RHS side, you will get 1 minus p, which is more than 0, right? So let me write here itself, since p less than 1, right, that implies 1 minus p is positive, is more than 0. So once 1 minus p is more than 0, this is positive, infinity power positive is infinity, so therefore this directly, which is infinity. So therefore for p less than 1, the integral value is infinity, right? So therefore for p less than 1, for p less than 1, p less than 1, integration 2 to infinity f of x dx, f of x dx is divergent, because integral value is not finite. So therefore the corresponding series n is running from 2 to infinity 1 upon diverges for p less than 1, right? For p less than 1. Next, equal to 1 case we have to prove. Okay, case 2. So case 2, p is equals to 1. Why I have not done here itself p is equal to 1? You go back. So if I write here p less than or equal to 1, what happens? Equal to cases I need to prove. So let us substitute instead of p 1. Then 1 minus 1 0, 1 by 0 is infinity. And here 1 minus 1 0, infinity power 0 is undefined. So overall this will be undefined you will get. Okay. So overall undefined you will get. That's what I am doing p is equal to 1 case separately. So p is 1, then you start the integral again separately. So that integration 2 to infinity f of x dx, which is instead of p you substitute 1. So integration 2 to infinity 1 upon x into ln x whole power p. But whole power p is 1, so that will be 1 directly. Okay, and this will be modular integration 2 to infinity. I want to modify this. I want to write like this: 1 upon x upon ln x. Okay, ln x dx. So does it remind you any formula? Ln x derivative 1 by x, which is in the numerator. So just recall the formula. I am recalling. Since integration f dash x by f of x dx, f dash will be numerator, which is the derivative of the denominator, right? Then direct formula ln f, right? Ln modulus of f plus some c. So this is a formula you have seen already in PUC. Same formula I want to use here, or directly if you don't want to apply this formula, let us take ln x is equal to u. Already I have done in integral test. Once you verify, take ln x is equal to u, then proceed, you will get the answer. No need to worry. Okay, or you can proceed like this, directly you will get the answer. So therefore ln of what will you get? Ln x. Ln of ln x. Because denominator is what? Ln x, right? So overall the limits are from where to where? 2 to infinity. 2 to infinity. Now this will be ln2, ln of ln2, ln of ln2, ln2 minus upper limit ln of ln infinity. So now overall ln of ln2 is fine, but ln of ln infinity is infinity, right? Ln infinity is infinity, again ln infinity is, so overall it will be minus infinity. Okay, so this is not finite. So therefore what I can say, therefore the integral is diverges. Therefore the integration 2 to infinity f of x dx diverges, because integral is not finite. F of x dx is diverges, diverges. So therefore the corresponding series also 1 upon n into ln n whole power p, where series is running from 2 to infinity. You can write like this also, n is 2 to infinity, or just 2 to infinity also you can write, is also diverges, for what? P is equals to 1. So therefore overall, final comment is, for p less than or equals to 1, the series 2 to infinity 1 upon n into ln n whole raised p is diverges. So hence proved. That's it. Okay, verify answer. Hope you have done already. So from now onwards, the logarithmic p series test converges if p less than 1, p more than 1, and the logarithmic p series test is diverges for p more than or equals to p less than or equals to 1. So depending on this, let's do some problems. So this problem already have done, which is problem number 3 in the last lecture. Look at once. So same thing, diverges. This is diverges for P less than or equals to 1. Just now we proved. So in a similar fashion, look at the problem what we had. So if you look at the problem, n into ln n, right? N into ln n means ln n power 1 is there. So therefore, series n is running from 2 to infinity, 1 over n into just ln n. So here ln n power we have to look at. Power ln n power is p, right? So ln n power is 1. So instead of p we have 1, right? So that implies here p is equals to 1. P is equals to 1. So therefore, by logarithmic p series test, by logarithmic p series test, logarithmic p series test, the given series, the given series, the given series diverges. That's it. So directly you can conclude like this. Or if you want to apply integral test, you can apply no problem, whatever. So many ways you can conclude. This is the simplest way. Logarithmic p series test is the simplest way, and you have to take care the terms of the series, the nth term of the series should be in that correct format only, n into ln n whole power p and 2 to infinity. Then only we can apply logarithmic p series test. Similarly, second one, problem number 7, continuation. Look at here, n into ln n, n into ln n, what we had, L into ln n whole power 2021 is that. So instead of p, we are having 2021. So therefore, so directly, what we can say, so 1 over n into, right, n into ln n whole to the power of 2021. So this is series, n is running from where to where, look at 2 to infinity. Yeah, it's perfect. So in here what we had, so p is equal to 2021 you had. So therefore, again by logarithmic p series test, so remember I am telling only converges, I am not giving the perfect sum. What is the sum? In this test we can tell only status, converges or diverges. Converges means what? This sum is finite. What is that finite? We don't know. We cannot say. By this test we cannot say. Only we can tell is the sum is finite or not. Yes, this sum is finite. That's it. Okay. So this is first method, and you can do it by second method also. Okay. So this is first method. This is first method called first method. Okay. Next, this is second method. Second method, don't apply logarithmic p series test, you apply integral test. Okay, try once. So by integral test, by integral test. That means you verify all the three conditions are satisfying for integral test, and later you take ln n is equal to u. Then you will get it easily. Try once, okay, and take it exercise. Try once. Next one, theorem number 7, the comparison test. So first in this we want series with non-negative terms we want. Okay. So what is meant by series with non-negative terms? So look at here. If the terms an's are more than or equal to 0, then we can say that these are non-negative terms. Positive terms means what? Positive terms means an is strictly more than 0. Okay. Non-negative here. Non-negative means what? The terms which are not negative. Indirectly more than or equal to 0. So 0 is neither positive nor negative, right? From 0 onwards, the terms are called non-negative terms. Now look at the first conclusion of first statement of the theorem. Series an converges if condition is there is a convergent series Cn. Okay, there is a convergent series Cn with an less than or equal to Cn, an less than or equal to Cn for all n more than or equals to capital N for some natural number n. That means what? After some index, terms should satisfy this condition. See, first few terms are not satisfying, no need to worry. but after certain stage, for example from third term onwards or fourth term onwards or fifth term onwards, infinitely many terms need to be satisfied in this condition. Okay. Similarly, the second statement, series an diverges if there is a divergence series dn of non-negative terms with an more than or equals to dn for all n more than or equals to capital N for some natural number n. Okay. So in this, if I want to conclude an is diverges, I need to find a proper lower bound which is divergent lower bound. If series dn diverges, then obviously upper bound is diverges. In this, if upper bound is converges, obviously lower bound is converges. That's what the theorem statement. Let's look at the proof. Listen carefully. Proof. First one, given that what is given to us, series Cn is converges. Series Cn is converges. And what is given, Ans are less than or equals to Cns. Okay. For all n more than or equals to some capital N where n is natural number. So this is given to us. Then we have to prove that. Series An is converges. Okay. Then we have to prove that series An is converges. Okay. So this one we have to prove, right? So then start with assume this is inequality number 1. So then 1 implies what I'm going to do is, so an less than or equal to Cn already given to us for all n more than or equals to some capital N. N more than or equals to capital N means what again here? So what are the possible values of this n? So small n takes capital N, right? N plus 1, right? Comma n plus 2, comma n plus 3, comma up to so on. So these kind of values this n can take because more than or equals to capital N, right? So therefore, let us construct the inequalities an less than or equal to c capital N and an plus 1, this one is less than or equal to c n plus 1, okay, and an plus 2 is less than or equal to c n plus 2 and up to so on. Okay. So assume this is number 2 and this one is number 3 and this one is number 4. Okay, next step, I want to add all these inequalities. Then what I will get, just look at. So inequality number 2 plus inequality number 3 plus inequality number 4 plus up to so on. Infinitely many inequalities I'm going to add. Then what I will get, an plus an plus 1, okay, plus an plus 2, right, plus up to so on, less than or equals to Cn plus Cn plus 1, right, plus Cn plus 2 plus up to so on. Okay. Then this can be written as series n is running from capital N to infinity. Can I write check once? An. If you're getting doubt, you can run the series. Now substitute small n is equal to capital N here. An plus an plus 1 plus an plus 2 like that up to so on. So these terms only will get, which is less than or equals to series n is running from capital N to infinity Cn. Okay. And what is given to us? Given that series Cn is converges. Let's say series Cn is sum, right? So therefore, if some series is less than or equal to 3, I cannot say that it is converges. But provided here, what kind of ans here? Here ans are more than or equal to 0. So once ans are more than or equal to 0, this sum is not negative. The sum is always more than or equal to 0. Therefore, such kind of minus infinity sum is not possible here in this case. Okay. So therefore, here no need to worry. So the sum is always more than or equal to 0. A number which is more than or equal to 0 but less than some finite L. Therefore, this is also finite. So therefore, series n is running from capital N to infinity an is converges. That's it. This only we need to prove, right? But moreover, what we have to prove is series. I need to prove that this series is converges, right? Series n is running from 1 to infinity, an is converges. But here n is equal to capital N to infinity is there. So indirectly some terms are missing here. Which terms are missing? So a1 plus a2 plus up to so on plus a n minus 1. So these terms are missing. But these are finitely many number of terms. Already this is converges. For example, look at here. Let us consider this series. Series 1 upon 2 power n minus 1. Let us take this series. N is running from 1 to infinity. So this is a geometric series which is converges to a by 1 minus r. A means 1 by 1 minus geometric ratio is half. Therefore, sum is 2. You expand this, what you will get? 1 plus 1 upon 2 plus 1 upon 2 square plus up to so on, right? So this sum is 2. So if I am adding few terms here, like for example 4 I am adding, some 5 I am adding, some 10 I am adding, for example. These 3 terms I am adding extra. So here also 3 terms you need to add. 10 plus 5 plus 4. So indirectly, what is this? 12, 17, 21 is the sum. So therefore this series sum is how much? 21. But this is finite, right? Because finitely many terms you are added. Here also same. Infinitely many terms sum is finite. These are infinitely many terms. Look at a1, an plus 1, an plus 2 up to so on infinity. So infinitely many terms sum is finite. We are adding few terms, a1, a2 up to so on an minus 1. Few terms we are adding, right? So this sum is also finite. So overall, so therefore conclusion is, therefore series n is 1 to infinity an now. 1 to infinity an is converges. That's it. This only we need to prove. Okay. So this is a first statement. Similarly, second statement. What is second statement? Again, same story. Given that series dn diverges. This is given to us, diverges, and what is given? And ans are more than or equals to dns. Okay. This is for all n more than or equals to some capital N. This is given to us. Then we have to prove that. Then we have to prove that series an is converges. Okay. Again, same story. You assume this inequality is number 1 in this. So assume this is 1. This inequality is number 1. So this is 1. So from 1 implies again in this. So inequality number 1 implies, what is that? ans are more than or equals to dns. Okay. So from here, what I can say that you expand it. N belongs to natural number set, and n is more than some. Okay. Let me write this. For all n is more than some capital N. Okay. Now expand it. So after expansion, what will get here? So a capital N is more than or equals to d capital N, and a capital N plus 1, same like first one. Okay, more than or equals to d capital N plus 1, right? So a capital N plus 2 is more than or equals to d capital N plus 2, so up to so on. So if you add all these things, so assume this is it is 1, okay, and this one is 2, and this one is 3. Already 1 is over. Let us call this is 2, and this is 3, and this is 4. So the next step, what I am doing is I am adding all those inequalities. 2 plus 3 plus 4. If you do all these things, so what will get? Infinitely many inequalities I am adding. So directly I am writing series n is running from capital N to infinity ans, and this is more than or equals to series n is running from capital N to infinity dns. So already this series is diverges, right? So this series, once this series is diverges, so therefore what I can say, the sum is infinity. It cannot be minus infinity. Why? Because all dns are non-negative terms. Once non-negative terms you have taken, if you do the sum, you will not get negative number. Sum will be always more than or equal to 0. Let's call the sum is infinity. So once it is infinity, then what I can say? So series n is running from n to infinity, right? Ans. So this is also more than or equals to infinity. That means what? This sum is infinity indirectly. More than or equals to infinity means what? It is also infinity. So but it is n to infinity. That means if you add few more terms, like n is equal to 1 to capital N minus 1, you add, If you're adding those terms, what will get? Again, this is infinity, more than or equals to infinity only. We're adding extra, right? So that become infinity. So therefore, finally, what I can say? Therefore, this sum is diverges. So therefore, series n is running from 1 to infinity. Okay, 1 to infinity. An is diverges. This is diverges. This is diverges. That's it. So therefore, roughly I will explain. If you're having a convergent upper bound, okay, if we are having a convergent upper bound like this, an less than or equal to bn, cn, if this series is converges, then obviously this lower bound is converges. Okay, and next one, if you're having a divergent upper lower bound dn, if this is diverges, then obviously this is also diverges, because if the sum is infinity, the sum is more than infinity means this is also infinity, like that. Okay, so that's what about comparison test. Then look at a few problems depending on comparison test. Look at this problem 8. Find the convergence status of the series n is running from 1 to infinity 1 upon n squared plus 1. This problem already I did in integral test. Look at integral test first problem. So you can do this by two methods. By first method is by using integral test. So first method, second method. Okay. Now in this second method, what is given? Series n is running from 1 to infinity 1 upon n square plus 1. N square plus 1. That means here, what is an? An is 1 upon n square plus 1. 1 upon n square plus 1. Okay, n square plus 1. So what I'm doing is, now I'm going to establish a relation now here. So look at n square plus 1 is always more than or equal to n square, right? This is always true. For all n belongs to natural number set. Whatever the natural number you take, this is always true. Now reciprocal this. So 1 upon n square plus 1 is always less than or equal to 1 upon n square. Is it? Yes, it is. Or indirectly what I got, so this is an less than or equal, let's call this is some cn. Okay, this is an only, right? Look at this is an. So an less than or equal to cn. So now what is series cn? So series cn is equals to series cn is 1 upon n square. Nothing is given means n is running from 1 to infinity. Okay, 1 to infinity is converges, right? How it is converges? Can you guess? It is converges by P series test. Recall P series test. All the series you should remember. All the test you should remember. What it says, P series. So therefore, what is P series test? So n power P. So this series is converges, right? For P more than 1, and diverges. The same series diverges for P less than or equals to 1. So in this case, P is 2, therefore this converges by P series test. Okay. So therefore, by comparison test, clearly by comparison test, by comparison test, the series, okay, the series 1 upon n square plus 1 converges, is converges. So this is by comparison test. Okay. So let me recall one thing so that it will be very clear. For example, so look at the same series, same term n square plus 1. This is always less than or equal to 3, right? It is true for all n. For all n it is true. For all n belongs to natural number set, right? So now you treat this is like an and this is like cn, right? That means what? Series cn will be here what? Series 3. Cn is 3. But what is this? Series 3, it will be infinity. Therefore it is diverges. That means what? You are having a divergence upper bound. That means, so series an is less than or equal to infinity, right? Because series cn is infinity. That means what? Series an is less than or equal to infinity. Now can I say that this series is finite? I cannot say that this series is finite. Why? Because this series may be infinity minus 1, right? If this series is infinity minus 1, so infinity minus 1 is less than or equal to infinity. That means the sum of all the terms is infinity minus 1. We don't know what is the sum exactly, right? So then in this case it is diverges. The series is some 5. Phi less than or equal to infinity is true, right? Then in this case it is converges. So now there are two possibilities. One is infinity minus 1 and one is phi. So therefore, if something is less than or equal to infinity, we cannot say that this series is converges. Okay, that means such kind of divergence upper bound here cannot work out. We want always convergence upper bound only. So this is converges. Then hence the lower bound is always converges, provided the terms are non-negative. Understood? So it's like sandwich. We need to find the proper upper bound and proper lower bound. What kind of proper upper and lower bounds in sandwich theorem? Both should converge to the same limit. Same kind of here. In comparison test, we need to find proper upper bound, which is convergence upper bound we want, particularly in series, not in sequence. The corresponding series should converge. Then only the lower bound is converges by using comparison test. Hope you understood. And with this, I will stop.